The title of my lecture is Macfarlane quaternions. I'll tell you about alternative type of quaternions which are practically not discussed in the literature. The plan of my talk consists of several points. First, I would like to recall you about properties of Hamilton quaternions and Gibbs-Heaviside vector algebra. Then I'll tell you about Macfarlane quaternions and via relationships with Pauli and Dirac matrices. So, Hamilton quaternions. Quaternions were invented by William Hamilton in 1843. Quaternion is the four-component value which consists of scalar part and vector part. The values A1, A2, and A3 is the basis elements of quaternion. They have specific the multiplication rules. The squares of basis elements are equal -1. If we multiply A1 on A2, we obtain A3. But if we multiply A2 on A1, we obtain minus A3. The algebra of the basis elements is anticommutative. These rules can be represented in the following table. Here, if we multiply A1 on A1, we obtain -1. If we multiply A1 on A2, we obtain A3. And if we multiply A1 on A3, we obtain -A2. The main advantage and the main properties of algebra of quaternions is the existence of so-called Clifford product of vectors. If we consider two Hamilton vectors A and B and consider the direct multiplication of A and B vectors, we obtain the following expressions. This is so-called Clifford product of vectors. If we define scalar product and vector product, then Clifford product of vectors is equal to the sum of scalar and vector products. This is a very important property which allows us to write many physical equations in a very compact form. However, in the algebra of Hamilton quaternions, square of vectors is negatively defined. This significantly complicates the geometric interpretation of basis elements. To overcome this disadvantage, Oliver Heaviside and Josiah Gibbs proposed alternative type of algebra, so-called vector algebra. They defined two different types of multiplication: scalar product, which is denoted by dot, and vector product, which is denoted by cross. The rules of multiplications of A elements of vector algebra is represented here. You can see that there is the scalar products, the rules for scalar products, and rules for vector products. In this algebra, the square of vector is positively defined. However, in this algebra, there is no Clifford product of vectors. This significantly limits the capabilities of this algebra. So, Macfarlane quaternions. Alexander Macfarlane proposed alternative type of quaternions. Macfarlane quaternions consist of scalar and vector part 2, but the rules of multiplication of A elements is different. The square of basis elements are equal to 1. If we multiply A1 on A2, we obtain not A3, but A3 multiplied on I values. where I is the imaginary unit. These rules can be represented as the following table. If we multiply A1 on A1, we obtain 1. If we multiply A1 on A2, we obtain IA3. If we multiply A1 on A3, we obtain minus IA2, and so on. In this algebra, square of vector is positively defined. And of course, in this algebra, there is Clifford product of vectors. There is a very simple relationship between basis elements of Macfarlane algebra and Hamilton algebra. In 1927, Wolfgang Pauli proposed so-called sigma matrices, which is named now as Pauli matrices. The algebra of these matrices is the same as the algebra of Macfarlane quaternions, you see. Square of sigma matrices are equal to 1. If we multiply sigma 1 on sigma 2, we obtain I sigma 3, and so on. Pauli used this matrix algebra for the factorization of energy operator. This allowed him to describe the spin properties of electrons. Momentum is represented in the basis of sigma matrices, and the energy operator is represented as the product of two terms. In 1928, Paul Dirac used practically the same algebra to factorize the operator equations for energy and momentum, relativistic equation. He used two types of matrices, rho matrices and alpha matrices. The algebra of these matrices practically the same as the algebra of basis elements of Macfarlane quaternions. Algebra of Macfarlane quaternions is the base for the space-time algebra, which is applied for the description of electromagnetic field, weak gravity, hydrodynamics of vortex flows, hydrodynamics of plasma, electrodynamics of superconductors, and for description of baryon and lepton fields. As a conclusion, I would like to recommend you our book, Space-Time Sedions and Via Applications in Relativistic Quantum Mechanics and Field Theory. This book is available through the internet. And thank you very much for your attention. If you have any questions, or maybe you would like to discuss something, you may write me using this email. Thank you very much.